All right, it's my pleasure to introduce our speaker today, Krista Lynn Smith. Krista did her undergraduate studies at UT Austin and then a PhD at the University of Maryland and NASA Goddard. She then went on to be a postdoctoral Einstein Fellow at Stanford University and was then faculty at SMU and is now at Texas A&M University. And she'll be telling us about a dynamic panchromatic look at supermassive black holes.
All right, yeah, thank you, Cynthia. I think this is working. Is it switched over? Okay, good. So thanks so much for the invitation. I've never been here before, so this has been great, and I got the grand tour of the campus. It's amazing, a lot of historic stuff going on. I'm going to talk about Through the Kaleidoscope, and I picked that metaphor carefully because just when you look through a kaleidoscope, what you see is lots of colors, but you also see how the relationship between those colors changes with time. So when you turn the kaleidoscope, all of these kind of funny shapes happen, and the colors change and their relationships to each other change. And what I'll tell you about today is that we can actually use a similar relationship between different types of light, or different colors, if you will, to study supermassive black holes and the phenomenology of accretion and jets. And then I won't have time today to talk about kind of a different aspect of my work, which focuses mainly on radio mapping of star formation and AGN feedback. So if you are interested in that, I'm happy to talk about that with you this afternoon if you have some time. But I'll be talking about my time domain stuff today. Okay, so just as a quick overview, supermassive black holes are black holes with masses between 10 to the 6 to 10 to the 9 times the mass of the sun. The origin of these black holes is not known. We have a lot of interesting ideas, but we don't exactly know how they come to be and why they come to be where they are, which is at the centers of basically every major galaxy. We're not sure how far down into dwarf galaxies this statement goes, but for the most part, it seems pretty much a sure thing that there's a supermassive black hole at the center of all spiral and elliptical galaxies. And our own galaxy is not an exception. Hello? Yes. Our own galaxy is no exception. So if you look to the south in the summertime from this location and look right in between Sagittarius and Scorpius, you'll be looking towards our own galactic center. And in the galactic center, very careful maps, which are shown here, you can see the year advancing in the top right, show stars that are orbiting around something at the position of that white star over these many years of observation. And we can use pretty basic stuff like Kepler's laws of planetary motion to determine the mass of the thing that they're moving around. And there's no optical emission coming from that location. But if you do the math, you find out that these stars are orbiting something with about 4 million solar masses, which doesn't give off optical light, doesn't give off much light of any wave band, although a little. And it's very small. It's smaller than our solar system by a good amount. So this has to be a black hole. That's the only answer. And the people who did these observations, the experiment I just showed you was run by Andrea Ghez, but Reinhard Genzel did something similar. And they basically proved the existence of a supermassive compact object in the center of our galaxy. I'm not sure why they didn't just say black hole. That's what it is. But maybe they were hedging their bets or something. So this was the recipient of the Nobel Prize in 2020, was the confirmation of the existence of the supermassive black hole in the center of the Milky Way. Now, this is not the Milky Way, obviously. This is a barred spiral galaxy, which is the type of galaxy we think the Milky Way probably is. And most of the time, supermassive black holes way deep down inside this black box here are what we call quiescent. They're just minding their own business, like any other hole. If you don't get too close to it, you don't fall in. It's fine. Quiescent, difficult to study, not giving off very much emission, like I showed you in the previous video. However, in about 10% of galaxies, and this number can be between 10% and 50, depending on which AGN scientist you're talking to, but in some fraction of galaxies, the black hole is not quiescent, it's what we call active. And it's consuming a large amount of matter and energy. and in doing so, generating a large amount of luminosity. Sometimes so large that it outshines the rest of the galaxy and just looks like a bright point source, which they called a quasi-stellar object when they first were discovered in the 50s and 60s, which is the origin of our word quasar. So that is what these objects are. They are quasars if they're very luminous, but the kind of more umbrella term is active galactic nuclei, as opposed to quiescent galactic nuclei. Active galactic nuclei, or AGN. A nucleus of a galaxy with a supermassive black hole that is actively accreting matter. So now, if we zoom way in, deep down into this box, we can see in what is my favorite ever artist's rendition of an active galactic nucleus. These have really come a long way since you had to find them on like DeviantArt in the early 2000s. Of what that engine looks like, the kind of central engine of an active galactic nucleus. So the black hole is where you would expect, right down there in the middle. And there's a disk of material that's falling into the black hole, just like water falls down a bathtub drain. And it's swirling as it goes in. So it forms this accretion disk. There is a bright population of relativistic electrons just above probably the middle of the disk. We can't resolve this structure. So we're inferring the geometry. There is an X-ray emitting source that is very small, that is very close to the black hole. And we believe it to be relativistic electrons giving off synchrotron emission here in the corona. So that's what we call it. We just call it the corona because we don't actually know what it is. It's a big field of study, what exactly the geometry of this population is, but it emits X-rays. And then around the whole shebang is this dusty, puffy object called the torus. It can't come in closer because the dust becomes sublimated by the powerful radiation of the nucleus, but it's kind of this clumpy, cloudy structure, which may or may not be continuous like this. It may actually be discrete clouds. But the upshot is that it blocks the view of the accretion disk and the corona from some viewing angles. And then there is a relativistic powerful jet in some, most, a few, depends again on which scientist you talk to, that is emitted and powered by the rotation of the black hole and the material that is accreting into it. This is an important distinction. The jet does not come out of the black hole. The press says this all the time, and people ask me about it all the time. On like Ask an Astronomer, they're like, I just read that there's stuff is coming out of a black hole at like 10 times the speed of light. I'm like, there's so much wrong with that statement. It's hard to get into. But the press says often that the black hole is shooting things out of it. It's the material that's accreting in that has become entrained in a flow, which is probably collimated by magnetic fields. Anyway, there's a jet perpendicular to the accretion disk. Now, each of the pieces of this engine emits in a different waveband, primarily. So the disk around a supermassive black hole emits in the optical and ultraviolet. As I said before, the corona emits primarily in the X-ray. The torus absorbs the high energy emission here and then re-radiates it. The dust in the torus re-radiates it as infrared emission. And the jet actually gives off all wavelengths, but is brightest in the radio because of the synchrotron emission, but also it can be quite bright in the gamma rays if you happen to be oriented, your viewing angle, such that you're basically looking down the barrel of the jet. And that's what we call a blazar. That's a special type of orientation. The same object, but tilted towards us, and it's a rare orientation, but I'll talk more about blazars later. And so if we're fortuitous enough to be looking down the barrel, we do see gamma rays. So each piece of this engine emits primarily in a different waveband, which means that we have to use different tools to study each of these pieces, and we have to use a kind of arsenal here of observatories. So optical, this is TESS. We're going to talk a lot about TESS shortly. The Discovery Channel telescope at Lowell Observatory. This little guy I use a lot. This is NICER. It's on the International Space Station. It's an X-ray timing instrument intended for neutron star stuff, but actually really good at X-ray timing of AGN, X-ray spectroscopy. It's a useful little thing. It's about the size of a washing machine. Radio, which this is the VLA. This is what I primarily use for my feedback studies. Infrared, you have a few options because you have to get up above the atmospheric opacity level. So you can either build it up on a mountain. This is Keck IRTF. You can fly it in an airplane like Sophia, or you can go into space like Spitzer. And then this is Fermi Gamma Ray Telescope up at the top. So in order to understand these nuclei, you need this huge array of different types of telescopes to study each piece of that puzzle and then put them together. Now, putting them together requires you to understand one other important thing, which is that active galaxies, this central engine, is variable, very, very variable at all wavelengths. So this is the same object in not simultaneous data, but the same object in all three plots. This is an optical light curve, brightness versus time. And you can see kind of some flares here, and then it kind of is static for a while. This is old from 1963, when this was actually the first AGN light curve that was published. Then this is a radio light curve of the same source. This source is a blazar. This is the kind of source where you're looking down the barrel of the jet. You can see some tremendous variations here, and this light curve is long. This is 20 years long. And this is a gamma ray light curve of the same source. Okay, the baselines are all different here, but you can see very significant variability at every wavelength that this has been studied at. Now, just a couple of terms for people who don't do time domain stuff too much, so no one gets lost. When I say light curve, what I mean is a plot of brightness in any unit versus time. And the Fourier transform squared of a light curve is what we call a power spectral density function, or a power spectrum. And what you get out of it is a plot of how much power is in the variability at a given frequency. Okay? It's basically telling you what and frequency, the inverse of frequency is time. So it's telling you what time scales in these light curves is there a lot of variability power. And one primary observable that tells us something about the underlying process is the slope of that power spectrum, alpha. So the slope of kind of this part that looks more or less linear and the higher frequency portion is one observable. So just so if I slip up and say power spectrum or power spectral density, you know what I'm talking about. Just a quick vocabulary recap. All right, so let's get into the cool stuff. So in 2009, NASA launched the Kepler mission. And the point of the Kepler mission was to look for the signal of a planet transiting in front of a star outside of our solar system. So it was looking for exoplanets. And in order to do this, it looked at one patch of the sky. So here is this funny polygon shape is the Kepler field. And it's pretty big. This is the constellation Cygnus, so it takes up a good chunk of the sky. And it didn't roam around and point the way telescopes often do. It stared at that one patch for 4 years and didn't look away. And as it did that, it took a 30-minute image of sources in that field that people proposed. So it didn't do it for the whole field. You had to ask. But they monitored by default tens of thousands of stars to look for this signal. So the light curve is shown at the bottom. It's constant, and then as soon as the planet blocks a little bit of light, it dips down, and then it becomes constant again. And this is a very hard signal to see, because it can be parts per million. For small planets, it can be very hard to see. So you need ridiculously good photometric precision. So the Kepler spacecraft had at that time an unprecedented photometer. We had never built anything like that before. The cadence was amazing. And the baseline was years long. And so this made it an excellent engine for finding exoplanets, and boy, did it ever. Thousands and thousands and thousands of planets were found. It was a huge success. But that's not what I wanted to do. I wanted to use this instrument to study this galactic nucleus, to see what is going on in the optical emission coming from the material falling into the black hole. So the Kepler field, here's a zoom in of the Kepler field. The Kepler field was really close to our galaxy plane because they wanted to find planets in our galaxy, which is reasonable. But that meant that it didn't overlap with a lot of extragalactic surveys where AGN would be known. So I used SWIFT here as part of my PhD thesis, an X-ray imaging instrument to scan 4 modules of the Kepler field of view to survey them and look for AGN, and we found some. And I called that the Kepler Swift Active Galaxies Survey, or K-SWAGS. It ended up getting actually another S, of being the Kepler Swift Active Galaxies and Stars Survey, because some of our X-ray sources were very interesting to stellar people who wanted to learn about like active M dwarfs and stuff. So it turned out to be kind of useful, kind of cool. And then we asked Kepler to look at those sources that we found. And these are some light curves that we got from Kepler. The baseline on this one is 4 years. This one's a little less than 2 years. And I just show these because they're kind of examples of the types of variability that we see. So rapid stochastic variability is seen here. You can see these kind of quick variations. In the middle light curve, it looks non-variable for a long time, like a year. It's a fainter light curve. And then there's an event that occurs. I don't know what that is. An event occurs, and then it goes back to being more or less constant. And then in the bottom light curve, you can see kind of a superposition of those behaviors. So rapid variability, but also sort of longer-term, slower variations. So this is just an example of some of the stuff that we were looking at. And what you can do without getting too much into the nitty-gritty is you can model some of these oscillations. You can learn about turbulent eddies in the accretion disk. You can learn about viscosity and magnetic reconnection flares, which are kind of cool and can happen sometimes and cause some of these more rapid variations. And then how these perturbations sort of propagate inward through the accretion disk towards the middle. So the origin of optical variability in accretion disk is a superposition of a lot of things. It's bulk accretion rate changes, so you just have more material falling in, but that's really slow. Those are long time scales. Then you have turbulence, flares, magnetic turbulence, reconnections. That's weeks, days to weeks, and then you have reprocessing of all the rapid stuff going on in the corona, which can be very fast indeed, like minutes. Yeah.
This is a naive question, but yeah, I noticed with your rest frame time scale there.
Yeah.
I mean, if the dynamic, like the phenomenon that are occurring so close to the black hole, like time dilation is crazy, isn't it? So, I mean, how much does that complicate even figuring out what your model should be if you see something happening very slowly in its frame, it would be happening very rapidly? Or vice versa. Wait.
So it actually depends. So you're right. So when we're looking at optical emission like this, it's actually far enough out in the disk that it's not too affected by gravitational redshift. But if you were looking at UV or soft X-ray, you're in the well. So it does matter. The other complication that's related to what you're saying is that if your variations are coming from the jet and it's pointed at you, then whatever you see happening at days timescales is really happening on years timescales, because the jet is Doppler boosted towards you. So yes, you do have to account for these things in your models. By rest frame here, all I mean is that I took the redshift of the galaxy out, like the cosmological redshift. But yes, if you're worried about if you think it's coming from the coronal reprocessing, you have to do like detailed ray tracing and stuff to overcome the relativity. So yeah, it does matter. Good question. So in 2013, Kepler briefly died and changed into something else called K2, which I won't get into. Really hard to use K2 data for AGN for complicated reasons. But TESS, the transiting exoplanet survey satellite, is the successor to Kepler. Still, as you can tell from the name, its main goal was to find exoplanets because of using the transit method. The cadence is similar to Kepler. It started out with 30-minute cadence. Then in the second 2 years, it went down to 10 minutes, and now it's at 2 minutes, which is really good. The baseline depends on the sky position, but unlike Kepler's fixed small patch of the sky, TESS's sky coverage is essentially the entire sky, with the baseline depending on where you are. So most of the sky gets 27 continuous days, but some regions near the ecliptic poles can have up to a year of continuous data. The magnitude limit is pretty bright for us. 19 is generous. It's probably more like 17 and a half. But if it's really variable, you can go fainter. This is tough for AGN. Most of them are fainter than this, but there's many thousands that are brighter. So it has its pros and cons, but overall it's an improvement on the Kepler mission. So let me just show you some of the mechanics of the TESS spacecraft here. So it has 4 cameras. I'll just go back. These are the 4 cameras. And each camera actually sees a pretty large portion of the sky. So it's going to show you the bottom camera first. And then there's 4 different fields of view, and they're vertically stacked on top of each other. And they're very wide across. So they're 24 degrees square, and there's 4 of them. So the patch of the sky that it's looking at every 2 minutes for 27 days is really large. And look that this is bigger than 90 degrees. That's going to matter here in a minute, that this actually leans backwards just a little bit. Now, this is one 27-day sector. So for 27 days, it takes an observation every 2 minutes of the entire thing. And this is it looking down at the south. And then after 27 days, it moves. And it does this every month. And it goes around. And because it's more than 90 degrees, you get overlap at the bottom and top when it flips over. So now it's going to flip over and do the northern hemisphere the same way. This is over the course of a year each. So you get a year of coverage at the ecliptic poles, and then you have basically an all-sky, high-cadence optical time domain survey. This has been really useful for a lot of cool stuff. This is just the stuff I'm interested in. It's also been successful at all the planet stuff, cool astroseismology, all kinds of kind of really neat applications. A lot of new asteroids have been found. But I like to use it for a few things I will talk about and some things I won't have time to. So searching for binaries, I will show a little bit of that because I think that's especially cool and timely with all the gravitational wave stuff. The universality of accretion. So this is an accretion disk around a stellar mass black hole that results from the death of a star. And that accretion disk is fed by material from a companion, stellar companion. So the question is, does accretion onto black holes behave self-similarly from the supermassive scale down to the stellar mass scale? We think it should, but actually there's some indications that there might be something a little different going on. The physics of relativistic jets. So this is a blazar visualization. So if you're looking down the jet, as I said in response to the question earlier, you get Doppler boosted variability that actually doesn't come from the accretion disk. It comes from particle physics processes inside the jet. The corona, what is the corona? We can combine X-ray and optical light curves together and watch how they vary. And if the optical variability is reprocessing the X-ray flares, we'll see the X-ray go first and then the optical come after. And that can tell us about the causal relationship between the accretion disk and the corona, and also the length of time of the delay, once you account for relativity, can tell us the distance scales between the corona and the accretion disk. As I said at the beginning, we don't actually know how far down the mass scale these massive black holes in galaxies go. One way to look for black holes in the intermediate range, like 10 to the 5 solar masses, 10 to the 4 solar masses, in dwarf galaxies is to look for variability. This has been demonstrated by Vivian Baldassar and seems to be going pretty well. And then I have some cute ideas about looking for axion-like dark matter bosonic clouds around accretion disks, but I don't have time to get into that. So I'll just start by sort of pitching this pipeline that I wrote to try and make AGN variability with TESS more accessible. The TESS data are extremely challenging to use if you're not doing exoplanet stuff. There's a lot of community-developed software out there. None of it is idealized for AGN and stochastic variability, so I tried to make one. The aperture selection is fully interactive, so this is the map here. This is a map of the sky. The pixels are humongous. And so you can actually click which pixels you want in your aperture. It extracts the light curves. It lets you mask cadences. So if there's something screwy going on, this is an orbit gap. But if you saw something weird in your light curve like this, you could just mask it out. And then you can customize how many vectors you use to do the correction. It builds those into a hybrid matrix of different correction vectors. And it's all kind of boring unless you're one of the people who wants to talk to me about that specifically today, which is great. I love talking about it. But anyway, it's called quasar variability. And it is available on GitHub. The paper came out December of last year. So take a look if you're interested. It doesn't have to be AGN. You can use this to do all kinds of other things. It doesn't matter. It can do any light curve. So check it out if you're interested. And now I will show you some of the physical results that we get out of looking at these exoplanet satellite light curves of AGN. So now we've talked about AGN generally. We've talked about the instruments themselves. What have we actually found? Well, here is a light curve from Kepler. And this is the only light curve from Kepler in which we saw an oscillation that looked quasi-periodic. So you can see it by eye to some extent here. But this is the power spectrum. This is not the power spectrum of this object. This is not the power spectrum of this object. We would have been in a Nature paper if it was. This is a power spectrum of a stellar mass black hole in an X-ray binary. Now remember, I told you a power spectrum tells you how much power occurs in the light curve at a given time scale or frequency. And usually you kind of see just the power law here. But if you have a big spike, that means there's a lot of power at one particular frequency, which is a period. Okay? It's a periodicity. So X-ray binaries have lots of these things, QPOs, quasi-periodic oscillations. They're pretty common in X-ray binaries. You see them all the time. If you watch an X-ray binary long enough, a QPO usually appears, and there's lots of different subtypes of QPOs, and it gets a little subtle. But they seem to be pretty rare in AGN. People have tried to find them, depending on who you talk to. There's 0 or 4 candidates for quasi-periodic oscillations in AGN, and they're all in the X-ray. They're all in the X-ray. So we found this in the optical. Here's the power spectrum of this object. You know, it's not like a big spiky peak, but it's like a lump. It's a lump at 44 days, and that happens to be the oscillation period you sort of pick out by eye there. So why is it so hard to find these in AGN if accretion works the same way in X-ray binaries and in AGN? So you may first be thinking, oh, well, AGN are way bigger. Yes. X-ray binary oscillation periods, if you look at the axis here in hertz, are fast, multiple times per second. This is log hertz, and it's, minus 10 to the minus 6.5. So we're talking about hundredths of a second versus days. So we're already accounting for this much larger scale of the accretion disk. So are they actually rare? Are QPOs actually rare in AGN? Do they not happen? Or have we been looking in the wrong place, or we haven't had the tools to find them? So I'm pretty sure it's the second one. But remember, AGN accretion disks occur in the optical UV. Stellar mass accretion disks are X-ray objects. So if we've had the instrumentation for decades to make an hour-ish long light curve in the X-ray. We can do that. We've had it a long time. We can look at stars. We can pull this out. We have not had the ability to see weak timescales in the optical with many repetitions for very long. And the problem is, if you look at this variability, it might remind you a little bit of the light curves I showed you from Kepler earlier, which you can convince yourself that there's periods there looking by eye, and there aren't. And that's called red noise. It just looks like periodicity. So to be sure you have a period, you need multiple oscillations, and this is like almost a 3-year-long light curve. So we can see a 44-day period there in the optical where the accretion disk is supposed to emit in these objects. So have we just not had the right data? Or are they actually rare? That's the question we can answer with these data. Now, here is a plot. This was some work I did at Stanford with Bob Wagner, an undergrad named Celia Tandon, of known quasi-periodic oscillations in the literature. So on the left, I am plotting the frequency of the oscillation. So these are all stellar mass. These are the names of some X-ray binaries. Frequency of the oscillation, scaled by multiplying by the mass of the black hole, okay? And then the masses of these black holes are tens, 8 to 12, I don't know, X-ray binary masses, little ones. And the data points are the dots. There's different oscillations that pop up in these 4 objects, and there they are. And then these curves are different models for what might be causing these quasi-periodic oscillations. The dashed line is labeled ISCO, that's the innermost stable circular orbit. That means it's just a blob orbiting around the black hole. Simple. The rest of them are more esoteric and confusing. They're actually like resonances that can occur in the disk, almost like seismic resonances in the sun, but they occur in the accretion disk. And then, well, in any case, we won't go into the details for time, but the point is, these, except for these odd low frequency ones, the GRS 1915, the models kind of overlap with the oscillations a little. And now, this is exactly the same plot, but on a log scale, and I'll show you why in a second. Now, again, here's the same plot on a log scale, and I'm showing on this side, these are the AGN QPOs in the literature. Same models, the curves are the same models. On the right, the stellar mass ones on the log scale, and on the left are the supermassive ones. And they're not consistent with the models. They're down. They're down low. And the spins are all really high. Is that real? Ask Chris Reynolds if you want to know. He doesn't think so, but they do seem to be rather high. Some of them are a little less high. This one up here is the only one consistent with the ISCO, and that's in a tidal disruption event. So what's going on here? Is this a selection effect? I think so. I think these objects are unusual. I think that the only reason we even know about these QPOs is because there were really long X-ray light curves of these data in the literature, like in the archives. No one took them looking for QPOs. Why were they well studied in the X-ray? Because they're narrow line Seifert ones that represent an extreme accretion regime. So these are oddballs that have been studied heavily for that reason. And so we shouldn't draw conclusions about the AGN population from them. But if we find 100 more, and they're all down here, that is unusual. They're not consistent with the models, and they're in a different parameter space than the stellar mass ones. And this is a log plot, so it actually is pretty different. Anyway, so we are hoping to find more of these in the TESS data that we didn't see in the Kepler data, but we're also doing this with NICER in the X-rays to try to fill in this plot a little bit more and help compare to theory. So we actually have right now ongoing...
Krista,
yeah,
question.
Sorry.
Could you go back one slide?
I will try. I will use the
okay, yeah, thank you. So you said that, but I forgot. So for this GIS 1915 plus 105, this a few points below, you said it's a different accretion mode. Is that the low state or the high state?
Yeah, so this is actually something I want to understand better. Do you know this object well and all about what it's doing?
No, but you mentioned that the few points that's below is from a different state, right?
Yeah, it's from a different state. So, okay. These are multiple oscillations from different, multiple different QPOs that came up at different times in the same objects. And the 2 lower ones are actually kind of consistent with where the AGN are. So I was thinking, why are these particular ones down here? And when we looked at the spectra, they looked like they were in a lower state, a hotter X-ray spectral state. But then Bob was like, well, this, hardness intensity diagram isn't that diagnostic, and it's not that clear whether this is in some kind of very hard state or something. I got confused. The literature on the X-ray binaries was rough, because there's type A, B, and C low frequency QPOs, and then there's high frequency QPOs, which is all the ones these are. So I hope it would be really cool if these AGN were in a similar state to the low state that we see the stellar mass ones in. I would love that. If there's X-ray binary people here, help me. But yes, thank you. I don't know exactly why we see lower ones here, but it looked to me, although it didn't convince my co-authors, that it was in a slightly different state. But we weren't allowed to say it in the paper because it didn't convince that person either. Yeah.
So if the argument is these are selection effects and that's the reason you're not able to find these things, you of course have a way to simulate all of the data for any signal that you like. Why not assume a power spectrum, inject it into the data, and see where you can recover things, where you can't?
Right. So we did that a little bit, and we only did that not in the comprehensive way you're suggesting, but we did that in the sense of what gaps do to finding the data, right? And so it turns out that ground-based sampling, where you have, we assumed a certain latitude and said, or a certain declination, and we said you have 4 months of daily or weekly cadence, and then you have several months where you see nothing, and then we put in random weather gaps. And it killed about 70% of the periodic signals that we injected, but we weren't really accounting for the red noise on top of the periodic signals, and it wasn't clear what the ratio of those processes should be. But you're right, this is the right thing to do. And simulations are kind of the answer to see, for example, what cadence LSST should look with or something. Yeah. Very, very, very good suggestion, and I think it is worth doing. Sorry, I'm not good at the remote. Okay, so we actually have NICER and TESS simultaneously looking at Markarian 766 and REJ 1034. Those are objects with, the two objects with the best X-ray QPOs in the literature for AGN. So we're going to hope and see that QPO pop up again and see whether we see it in both the X-ray and the optical, or in just one. So stay tuned. We're working on it. My undergrad is learning how to, not my undergrad, my first year student, a grad student is learning how to reduce NICER data, which is easier than TESS, but still not easy. So let me get to the binary stuff, because this is cool. So, as we said, there is a supermassive black hole at the center of every major galaxy. And we know from beautiful images like these that galaxies merge together all the time. So if the galaxies merge together, eventually the black holes should merge together. And this is kind of an artist's idea of what that might look like. So when galaxies merge, so should their black holes. What can we learn from our current time domain surveys about the statistics of this source population, which is the source population for gravitational waves? Now, LIGO has seen the stellar mass black hole merger signatures, and we hope that LISA in the 2030s will see merger signatures from merging supermassive black holes, but not just the actual merger chirp, but there is a background of gravitational waves in the universe due to orbiting massive objects like this. And so understanding that background and the source population of that background, which is not black holes that are slamming into each other at the very end, but that are orbiting at different separations, is really important for understanding the interpretation of the LISA data once it comes. Plus, it's just fun to find them. So here is a really cool simulation of two black holes orbiting each other. Each one has its own accretion disk, a mini disk, and they are both accreting from a circumbinary disk through these little streams. Now, there's multiple reasons to expect oscillation, periodicity, in a light curve from a configuration like this. You have the Doppler boosting of the black holes as they're moving around each other, causing just a sinusoidal oscillation. Don't worry about the words. And then you have the streams which can collide with each other on a periodic timescale as well. So people went out and looked. They went out and tried to find periodicity in light curves. This for separations that are not merging imminently, that might merge in hundreds of years or thousands or millions of years, we're looking at periods of years, okay? A few years. And so if you're looking at this and thinking that that's not that convincing, you're not the only one. Lots of people aren't convinced. Here's the data. The data have the error bars, and then the best fitting sinusoid model is there. Here's another example of people doing it with early ZTF data. Now, I don't blame these people. You've got to do your best, and you have red noise, stochasticity, and periodicity in the same plot, and it's really hard to tell and get a lot of oscillations on human timescales. It's just tough. So there's candidates. There's a good number of candidates out there, and LSST will help us more with this, especially if we can idealize the cadence the way that was suggested here. But it's degenerate with red noise. It's really hard to tell what you're seeing. So it'd be great if we had a different signature, and we can exploit the curvature of space to do this through gravitational lensing. So this is a light curve down in the bottom right. Just a reminder, or if you're a student, maybe you don't know, if your telescope is looking at a background source, it looks normal. You have a nice flat light curve, and then a foreground object moves between you and the source. It can bend the light or bend space around it, and the light from the background source must follow the bend in space. So you end up with multiple images of the background source, and that gives you a flare in the light curve. I call that a lensing flare. Even if you couldn't see the multiple images of the source, you would see the light curve get brighter during the lensing event. It's kind of like passing a magnifying glass over a background source. So here's the observer's eyeball. You don't have to worry too much about the math here. Here's the foreground black hole, and here's a background black hole with an accretion disk around it. Now, if you are lucky, and things work out geometrically just so, it is possible that the foreground black hole can actually lens the light from the accretion disk around the background hole. In that case, the light curve you would see, this is a theoretical model by Dan D'Orazio at Harvard, you would see the normal periodic oscillation due to just the orbit of the holes, and superimposed upon that orbit at a particular phase, a flare from the lensing. There's also a secondary lensing flare if there's an accretion disk around the foreground hole. Now, the height of the flare depends upon the inclination of the orbit with respect to your line of sight, eccentricity of the orbit, and a few other things. But I saw Dan show these two plots at a Einstein Fellow Symposium, and he was also one of those at that time, so that's why I saw it. And I got kind of excited because I had this object in my Kepler sample that was kind of weird looking. It has all the regular variability that you expect, and then it had this thing. And I didn't know what this was. I published a paper not knowing what it was. I like just the paper of all the Kepler AGN light curves said, hey, there's something funky. I tried to fit it as a TDE. I tried to fit it as a extreme mass ratio in spiral, a supernova. None of it worked. So weird. I tried very hard to make sure it wasn't instrumental. That's not easy to do with Kepler, but I worked very hard to do that. And so I ran up to Dan after his talk, and I was like, hey, do you want to look at this light curve that I have? Because I think it looks kind of like your signal. So we wrote it up. We modeled it. So here is for a very eccentric orbit. That's why it's kind of a distorted sinusoid here. The red noise is still there. The accretion disk is still there, so you expect the red noise. And then this is a zoom in on the model of the flare as a self-lensing event. Now, for the mass of the holes, we had very little constraint. We have a single epoch mass of 10 to the 8 point something from the width of the H-beta line, but that's only one black hole. So yes, there's a lot of degeneracies here, but it remains the only self-lensing candidate yet. It's called spiky. They let us call it that in the paper. So it's called spiky. And the paper was led by Harvard undergrad Betty Hu. So this might happen again. It should happen again in 2020. Well, I guess 2024. Gosh. So we have people using LCOGT and stuff to wait for this flare if it happens again. But the flare is short. Look, these are days. So it's 15 days long, and so you got to have fast cadence, and no one's going to let us look indefinitely at this thing every day for the whole year. So we're trying. Anyway, that's spiky. So let me go on to the last time domain application I'll cover today, which is blazars. Again, this is when you're looking down the barrel of the jet, and we can study processes within the jet and the origin of emission in different pieces of that. So this is a blazar spectral energy distribution. That's a spectrum across all the wavelengths of light from radio to gamma rays. And you can see that there's kind of a double-peaked structure here. There's two humps in the SED. There's this low-energy hump, which is pretty well modeled by synchrotron emission from the jet. Looks pretty good. Models work well. And then there's this higher energy hump that peaks in kind of the X-rays and gamma. Now, where these peaks occur in the spectrum does shift back and forth. There's some subclasses of blazars with respect to that. But the physical origin of the high energy peak is more mysterious. It could be the same population of electrons responsible for the synchrotron emission are upscattering those photons and making them high energy. Or there could be something more hadronic going on. So photopion production could give off these photons, but could also create neutrinos, which we have seen now from blazar jets, and gamma rays, which we also definitely see from blazar jets. So it could be either, it could be both. But one way to understand this is to look at these jets in all those colors at the same time, right? And see which ones happen first, or if the variability is correlated. Because if it's the same electrons doing the low frequency peak as upscattering to the high frequency one, maybe you should see correlated variability there. So this is a TESS blazar light curve and a Fermi light curve of the same source, where we see the gamma ray emission preceding the TESS emission. And this is actually a TESS light curve of the neutrino emitting blazar TXS 0506. And then here is a paper by Zach Weaver where we combine TESS, which is down here. Just look at the sampling, goodness. And infrared data and X-ray data. And there's a few other optical wave bands, but they're so much uglier than TESS that I didn't put them on here. And we did some cross correlations here and found very little lag, actually, in BL lac itself. So we're trying to understand those data, and we need a bigger sample, basically. We need a statistical sample of different types of blazars sampled in the X-ray, optical, and gamma ray, and doing a large cross-correlation analysis. So that's something we're working on in my group, but in collaboration with a lot of other blazar folk. Here's some work by my graduate student, Ryan Dingler. He has gotten some very nice blazar light curves out of TESS and has created power spectra and fit those power spectra with interesting models, gotten those slopes, gotten some characteristic timescales for the jet. And then he has been comparing these different spectral subclasses I told you about that peak at different places in the spectrum. And the kind of blue and orange histograms here are those two different spectral populations, and there's just no difference at all in the power spectral slope of those two populations, which is kind of unexpected because one of those populations, called FSRQs, flat spectrum radio quasars, the names are terrible. They're archaic. They don't actually correspond to anything meaningful in the current model, so just ignore them. These type of blazar is thought to be kind of off-axis, so that we're seeing both the jet and variability from the accretion disk together in the light curve. That could also mean that the accretion disk is more powerful and the jet is a little less powerful. It's orientation plus this accretion state regime. And BL lax, another type of blazar, is expected to only be jet emission, which should be more rapid and more kind of flary than the accretion disk variations that I've shown you so far. So we did expect to see a difference, and we did not see one. So that was sort of interesting. This paper is in review. Nice referee report, shouldn't be too bad. This is interesting work looking at periodicities in blazars. I don't know if I can play this movie. It might be a link. Let me see if it'll work. I guess it won't. It doesn't matter. You can see this is a plasma. This is actually a movie of a plasma experiment in the lab at Caltech. And you can see a plasma jet here. And what it does when it plays is it kind of spirals and forms like a kink. And then the kink relaxes. And you can watch kind of this kink that you can see here kind of move up the jet and change its period. And these are power spectra along here, Lomskargel periodogram showing big peaks. Here is just where the period, this says period, it's teeny tiny in days. There's a nice strong 10-day period here and an 8-day period in this blazar spectrum, and then this one's kind of transient. This is the time axis of the light curve. It kind of appears later. And we see some time evolution of the period, which he believes to be this kink instability inside the jet that we also see in the laboratory. So this paper is out. There's two of them, actually. There's 2024A and 2024B finding similar stuff in two different light curves. Now, I guess I'll go past the movie slide. And just quickly, I'll say that this isn't just the optical in TESS. He's doing it in the radio as well. And in the radio, he has these long, beautiful light curves at 4.8 gigahertz and a few other frequencies. Sees the same thing, these peaks in the power spectra that correspond to periodicities. But also, he sees that the spectrum, this is now a spectrum, not a light curve, of the radio source as this kink is evolving is actually changing. So this is a year. The year 2007, this is what the spectrum looked like. And then when we saw the period begin, he started to see the spectrum flatten out and change. So we're working on modeling the physical reasons for this. And this paper is almost out. I gave it a year already because it's like we sent it back and it should go through review, but stay tuned. And then I guess I'll skip this and talk about this because this is more fun. The last thing I'll show you is recurrence analysis, which is our current angle we're leaning into because this is like a computing group of people who are interested in that. We're going to throw some machine learning at this problem. So recurrence plots are basically two-dimensional autocorrelation functions. It sounds fancy, but basically what it means is that you run two copies of the same light curve against each other, make a plot light curve on it's just time, the same time axis on the x and y axes. And when two positions are close to each other, when the autocorrelation function is high, you put a 1 in the matrix, and when it's not, you put a 0. And it gives you kind of this QR code looking thing. This is what a recurrence plot of random noise looks like. It looks like random noise. This is what a recurrence plot of two different sinusoids with different periods superimposed looks like. You see these diagonal lines. These are the two periods, and then there's resonances. And then this is a Duffing oscillator, which is a common model for explaining X-ray binary variability in the X-rays, just so you can see a few examples. With respect to AGN, when I saw Rebecca Phillipson show these recurrence plots back when we were both at Goddard, I thought this is what machine learning likes. Machine learning doesn't like power spectra or light curves. It likes pictures, right? Image-based classification. So I thought, why don't we use recurrence analysis to make QR codes of all of these different types of blazars or Seiferts or whatever. And then we set loose machine learning image classification algorithms to see if there's actually differences in more subtle aspects of the variability than the power spectrum can see. So Rhine does not see power spectral differences here. That's unexpected. But Rebecca Phillipson, whose name is not up here, Rebecca Phillipson has shown that recurrence analysis actually does see subtler aspects of the variability than power spectra can. So here's a simulation of a damped harmonic oscillator, which is a model that's often used to describe jet-like variability. Here's a simulation, a light curve of the damped random walk, which is often used to describe disk-like variability from the accretion disk. And you can see they're symmetric over the diagonal, so I just show them on the same plot. The damped harmonic oscillator has these periodic style lines, and the damped random walk has a different sort of morphology, the sort of checkerboard. So we are working on creating these light curves, and we've done a lot of simulations of these things to see how well this is going to work on TESS light curves and hopefully ZTF light curves of both types of object to try and make the classification. So since that's perfect. We're done. Variability, especially when you do it across lots of wavebands, offers a unique observational window into high energy physics in the extreme space-time environments around black holes and also the extreme environments of particle physics in jets. With that, I thank you for your attention, and I'm happy to take any questions.
So that last point was really interesting with the, 2D recurrence thing. Those two plots that you showed, were those just from generated, simulated data, not from real light curves, or from simulated?
They are simulated, but Rebecca has done the analysis for that Kepler object that had the QPO, and she compared it to a Kepler AGN that didn't. So there is a paper out there. You can see a difference. So there is a paper out there doing just those two, but the Kepler AGN sample was really small. It was 25 AGN, so we couldn't do machine learning stuff.
What was that paper? It might be really interesting to...
Phillipson, Smith, and Boyd. 2020 or something.
Thank you.
There it goes. For the QPO stuff,
Yeah.
is it concerning that even for the X-ray binaries, where we kind of understand, seeing them more often, that they don't correlate with the spin?
Yeah, it is concerning. That is why there is still no accepted model for what's causing QPOs, because even in the ones we can see on human timescales, like on X-ray binaries, we can't explain them very well. We don't know if they're all from the same thing or if there's a bunch of different things going on. Like I said earlier today to someone, a lot of things go round and round in astronomy. So yes, it's a concern that we don't see a correlation with spin, because if it's related to the accretion geometry, maybe you should, right? But maybe we're not good at measuring spin.
Yeah, so, it's a thought more that it's the spins that are kind of smearing out an effect, or is it just maybe multiple of those effects co-added? Is there any sense of which it
I think that it's all of those things. When I started this comparison project to the stellar mass black holes, I thought it would be a lot clearer and we could use them as kind of a Rosetta Stone, and I was very wrong. That's still very, and that's the high frequency QPOs. The low frequency ones are even more mysterious, I think. So yeah, I think the picture is murky, if that's your impression, that you're right.
And can I ask one more question on the QPOs? So you had Swift J1644 up there, which is like the TDE one. I think there's a few other TDE QPOs. Are those just like lesser quality or different types? Or?
The reason they're not on that plot is because, unlike the booming one in the TDE, I didn't know whether they were low or high frequency, and we were restricted, and the Kepler one's not on that plot either because it was low frequency. So I wanted to stick with the ones that were in these resonances, these 3-to-2 resonances in frequency. But they should have been on there. The reason that one's interesting is because it's the only one that's consistent with orbiting around the ISCO. And so maybe TDEs are, like the QPOs you see in those are special for some reason in this temporary accretion disk that sort of forms. They're also I tried to see if there was a correlation between the existence of radio emission and whether it was consistent with the ISCO, because the TDEs probably form jets, like temporary radio jets. We see radio emission in some of them. So it's possible that the TDEs offer a clue. but yeah, the other ones, there was like 2 other QPOs, the TDEs. Yeah, so I mean that should be added in if we can possibly understand them, because they might be important. Transition disks or something.
Thanks.
So about that spiky, is it bright enough for the ETF?
It is, yes. The only trouble would be that we need it to do it almost twice a day to catch the flare. I mean, it's a 15-day flare. I guess we could do it every day and hope for the best. The problem is it's an expensive observation because it's been so long since the first flare was seen, which was in 2009 or 2008, 2010, that the model has smeared out when we expect it, because we don't know the eccentricity, we don't know the masses. So it's like over a 4-month period.
Okay.
But yes, it's bright enough.
The duration of that flare in that zoom in plot, I saw it was like more than a few days.
Yeah, it's about 15 days from end to end, yeah.
And because the model does predict some sort of quasi-periodicity even for the background level.
The underlying part, yeah.
So it'd be interesting to see if the ZTF shows something even remotely resembling that. But you have
that's a good idea.
You have the LCO-GT follow-up, so
yeah, that's
we'll know.
Right. So whether the eccentric sinusoid keeps going even if the flare doesn't.
Yeah.
Yeah, I'll ask the guys. I'll ask because I've just been waiting for them to send me a Slack message that says they saw the flare.
And
but that's a good point.
I also recall that maybe that was Luke Kelly had a paper estimating the probability of seeing such things. And it's much lower than much lower compared to seeing 1 out of 100.
So this is why. So yeah, and when Dan gave his talk, he said the same thing. He was like, it's like 1 in like 100,000 or worse. And so we had 25 Kepler AGN. So
pretty lucky.
Yeah, really lucky. But yes, I did tell that to Dan when I showed it to him. I was like, well, I know this is impossible, but like, look at this, And so he then did revise the probability estimate, but that was like after the fact. And so I don't know, you want it to make sense. I mean, yes, it's if those estimates are right, we got ridiculously lucky, like absurdly lucky. So that's a point against it. But the good news is it's supposed to happen over and over again. So, eventually we should know for sure. It's not supposed to be a one-off. Yeah.
So is the common? I sort of live in physics, so I am sort of trying to get a good understanding of what the consensus is for different variability sources for the AGNs.
The pizza has arrived.
Oh, great! Wow.
All right. Anyway, go ahead.
Is the consensus, you mentioned this a couple times, is the consensus that the source is damped random walk, or it looks like a damped random walk
For accretion disks.
for accretion disks?
I mean, it's well modeled by one. Whether that really means anything physically is less clear, but yes, it's a good model.
Okay.
Yeah.
Thanks.
Sure.
Yeah, about the lensing flare. So I didn't see the figure very carefully, but it looked like the DC level actually shifted after the lensing flare.
The what shifted?
The DC level.
Yep.
Is there a reason for that? Shouldn't it come back to the same position?
Well, I guess it's happening on the down part of the sinusoid, which is very eccentric. So you're kind of catching it. You're superimposing the flare on top of another oscillation, which is expected, but we aren't that sure of the form of that oscillation. Yay! Thank you. I assume that's for me and not for him. Okay. Okay. Great. So the good pizza has arrived, as I understand it.
Yeah, sorry for the delay, but the one will here. So if you can stick around, enjoy your Manolos. And let's thank Krista again.
Thank you very much.